Hi class, so here's our example problem. We had a fan that was hanging from the ceiling by a 2 by 2 by 1/4 hollow structural section, and we found that its natural frequency, the frequency at which it wanted to oscillate, was very close to the frequency of the fan that we're, let's say, planning to install. Let's say that we already have this hollow structural section hanging from the ceiling, and we are thinking about buying this fan and installing it, but we're not sure if it's going to do the job for us. We've heard that, based on our preparation document, we found that another important factor is going to be how much damping the system has. So we think about this fan system instead of just as a mass and spring as we had before. We had a spring attached to the wall, and then we had this mass. In reality, there's always some energy loss, and we draw that with a damper, a dashpot. They talk about these things, and they exist, where you've got viscous oil flowing through a small hole, and so the force that it produces is proportional to velocity. And you can find these things on doors, for instance, that stop doors from slamming, and actually on plenty of agricultural equipment as well. So this is a damper or a dashpot. And so in addition to the spring constant K, if we wanted to model this system, we would have to know what the damping coefficient C was. Sometimes the letter B is used. I'm going to use C. And that's a force that it produces per unit velocity, and it's opposing the motion. But we don't know what force it produces. It's easy for a spring. You can measure the force as a function of the displacement. That's a little bit easier to measure than the force as a function of the velocity. Also, unless it has a damper or a dashpot that looks just a discrete element like that, if you've got something that is just a piece of steel, what is its damping coefficient going to be? Sometimes you can't predict it very well. The best thing to do is just measure it. So if we can get a piece of hollow structural section and attach a large mass to it, we can estimate what the damping ratio is going to be just by watching its response. We know that the solution of the equations of motion of this thing, one of them is x as a function of time is a, the amplitude, and that's going to be the initial displacement that you give it, as long as you don't give it an initial velocity. That'll be the initial displacement, just like it was in the undamped case. E to the negative omega n zeta times time cosine of omega d times time, where a, again, is the amplitude, just as before. This omega n is your natural frequency, just like before. Same thing, square root of k over m. Zeta is new. This is the damping ratio. Might be the thing that we're trying to measure. You can measure C directly, or you can measure a little bit easier to work with, this damping ratio. Its definition, if you already know K and M and C, then you could find it, C divided by 2m omega n, or you could plug in root k over m and you'd find that 2 root km. So if you know k, c, and m, you can find out what the damping ratio is here. But if you don't know what one of them is, then you could find the damping ratio and then find out what c is, for instance, because c is the one that is probably hardest to predict. And finally, omega d is the damped natural frequency. It's a little bit less than the regular natural frequency. The natural frequency, omega n, times the square root of 1 minus zeta. Now, zeta, usually, if this system has this as a solution, it turns out it depends on what zeta is. Zeta has to be within the interval 0 to 1 in order for this to be a valid solution. If you had more damping, if C was really big compared to root Km, and this ratio were greater than 1, you'd find that this actually isn't technically the correct solution to the problem. There are other solutions that are basically decaying exponentials without the oscillation, without the cosine term. But if zeta is in this range of 0 to 1, which is what we're most interested in here, because it's probably going to be the case here. There's not too much damping that's built into steel. So that'll probably be the case here. We're going to have some sort of oscillatory solution, and zeta is going to be between 0 and 1. So if zeta is small, say 0.1, then, excuse me, this is 1 minus zeta squared. then 0.1 squared is 0.01. So this is 0.99 inside the square root, and the square root of that is even higher. It's like 0.995. So for moderate damping ratios, the damped natural frequency is almost the same as the regular old natural frequency. And this makes it really easy to go out and measure what the damping ratio and what the natural frequency of the system are, because you can just look them up on a plot of the response of the system. And so let's interpret what this equation looks like. Let's make a little bit of graphical sense for it. I've created a little calculator that you can use. And here I've plugged in the formula, e to the negative. I've used w instead of the Greek letter omega, and I've used z instead of the Greek letter zeta, but same idea here. And you can see here I've plugged in z is equal to 0. And when z is equal to 0, then this square root term is just 1, so we've got the natural frequency times x. And when z is equal to 0, then this exponential goes away. It just becomes 1. So you just are left with a cosine omega nt, or x, excuse me. I've used x instead of t here because that's what the calculator requires. So I've just got, the natural frequency. I've put in 3.14 pi. So that's going to make it go through pi of a revolution for every unit of time on the horizontal axis. So in 2 time, it goes through 1 complete cycle. And so as you change the frequency, it does what you might expect. You increase the frequency. Here I'll increase it to about 2 pi, and then it's 1 cycle per second. If I increase it down to 0, it becomes basically a flat line. We're going to bring it back to the center here. So this is the response of the undamped system. When the damping ratio is 0, it reduces to the equations that we had before for the undamped case. It's as though there were no damper there. It doesn't lose energy. Now, how does the damping ratio affect things? We've seen how the natural frequency affects the plot. And the damping ratio, watch this, as I increase zeta from 0, well, actually, before we do that, I'm going to turn on just these a exponential, this first part of the term. All right, I'm going to turn that on. These are kind of, right now, when zeta is equal to 0, right? This argument is 0, e to the 0 is 1. It's just amplitude and negative amplitude, negative a, which is 4. So these are just lines that kind of bound the outside of the solution. And in fact, when you increase the damping ratio and this exponential term starts to become important, you're going to find that this cosine curve is hugged and squeezed by these blue lines. So let's turn this off for a second, as we increase the damping ratio a little bit, you can see that these are decaying exponentials. Maybe it's helpful to just consider one, right? We're making a decaying exponential decay faster and faster by increasing the damping ratio, right? And so now we turn on a second one, we've just got symmetric ones on either side. You're going to find that all these do is squeeze the cosine term, squeeze the oscillations down. Let's turn this back on. And we see the oscillations occur between these two lines. And take a look, I said before that the damped natural frequency, which is going to be the peak to peak time basically, is one way of looking at the frequency. Look how as I change the damping ratio, it doesn't really change that much. I mean, theoretically it does. You can see that over here, the tops and the peaks here get a little bit off to the right. They're not perfectly aligned with the lines anymore. But for most practical damping ratios that you can easily work with, you're going to find that that's not going to affect things too much. So you can read straight from the graph. If I didn't show you this over here, actually maybe what I'll do is I'll change some settings and we'll see if you can figure out what the natural frequency is. Okay, so we can read off what the natural frequency is from this plot. We can see that over the course of 1.5 time, it goes through a full cycle. So the natural frequency is then, it's gone through 2 pi in a time of 1.5. Get around 4.18. Bring this back, let's reveal. Yep, 4.18, and it doesn't matter what the damping ratio is. If I change the damping ratio, I would have gotten just around the same answer. Okay, but how about the damping ratio? How can you figure out what this damping ratio is? Well, you could do that basically by ignoring the sine wave, or picking out the sine wave at the points where they intersect, where the two intersect is kind of at the peaks. And you can see from peak to peak over a time of 1.5 seconds how much the damping ratio lead to decay. What is the amplitude of this relative to that? And what is the amplitude of this relative to that? It turns out that that ratio is approximately constant, or it's exactly constant for a constant amount of time between peaks. So you can estimate from the graph, and I'll show you mathematically how we can do that in just a second. So let me actually go ahead and move this to something else. Okay, so here we see that the initial amplitude is 4, and the amplitude down here is about 1. So let's see how to find the damping ratio from that. It turns out that if you go through the math, you will find that for small damping ratios, the damping ratio is approximately the natural log of x1 over x naught. I'll actually write this in terms of the variables we have here. Let's write them as y, and I'll explain what those are in a second, divided by 2 pi, and we'll put a negative sign here. So y1 is the value of y at the first peak, and y naught is the value of y at the 0th peak. So on our plot here, the 0th peak is at 4, the first peak is at 1. And it turns out you can look at any two successive peaks. You can see that this is around 1.0 and this one is around 0.25. It's still a ratio of 4 to 1, 4 to 1, and it's going to continue to be a ratio of 4 to 1. So you don't have to be starting it at just the very beginning. All you need to do is find the amplitude at the first peak, or the height of the first peak, the height of the second one, and take the logarithm of the ratio between the two. So here, in our case, we have the negative logarithm of 1 divided by 4 over 2 pi. So that tells us our damping ratio is around 0.22. Let's see. Pretty close. 0.216 is what it is on this graph. I'm sure we could have gotten it a little closer. Now we're making a few approximations here, but these are good for small damping ratios. In the next video, we'll do our example problem. We'll do just another practice problem involving our actual fan support.